Let's go ahead and get started. Today is Tuesday, August 31st, 2021. We have a handful of stuff that we have to deal with. We're going to continue our discussion of the heart physiology. We left off last time talking about the cardiac conduction system and the electrical signal it produces, and we'll talk about what that does and the effects that it has. And then if we have time at the end, I'm not sure how long this lecture is going to take, we will start talking about some anatomy of our blood vessels, because after all, the cardiovascular system isn't just the heart. Still have a ton of homework to do for this section. That interactive physiology handout on the ECG is due on Thursday and is graded for correctness. It's okay if you haven't started it yet, because we will talk about those concepts today, and hopefully that will help you. And even if you have finished it already after today's lecture, you might want to go back and check it and change some things, because it will be graded for correctness. And also your PhysioX exercise 6 with 5 activities, so 5 lab reports. Tuesday next week, your unit 18 review, your cardiovascular exercise handout. That's that drop of blood that you're tracing through the heart and tracing through your body. That is also graded for correctness. And your PhysioX exercise 5 is due, which has 7 activities, so 7 lab reports. Thursday the 9th, your unit 19 review is due. PhysioX exercise 11, but just the 4th activity is due. And then you also have another blood physiology wet lab, lab simulator, not a wet lab, but lab simulator, which is our hematology labster. And remember, for full credit on those, you need to complete the entire activity and get it at least 80% correct. And remember, if you don't get it at least 80% correct, you do have the opportunity to complete it as many times as you would like to try to bring your grade up. All leading up till Tuesday the 14th, when we have our first lab and lecture exam. So that is the game plan. Any questions on anything's coming up or anything we've gone up to this point before we get started into new material?
For Labster, if we completed round 1 already and went back to just look at what we did, does that restart the assignment?
If you restart the assignment, it doesn't erase your previous attempt. So for instance, if you go into the, in Canvas, there is a Labster dashboard. And when you go on that, you are able to see your attempts. Claudia, I will double check that. But my understanding, when I set it up, you should be able to take it as many times as you want. So I will double check the settings on that. Let me actually write a note for that so that I don't forget. But when I set it up, I set it up as a learning exercise. So specifically, it could be repeated. But I will check that to see if that is indeed the case. So yeah, excellent. All right, great questions. Any others before we get started?
I have a question. I just wanted to see if maybe my audio was better. I was having trouble with it before.
Yes, absolutely. We can hear you perfectly now, Amanda. So that's spectacular.
Thank you.
Excellent. All right. Any other questions? All righty. Then away we go. Let's close this. Let's start the lecture. And bring up the lecture. All right. As I mentioned last time, we had talked about the 5 components of the cardiac conduction system. And we have talked about their functions, the specific characteristics of them, and why they're arranged in the fashion that we did. And as we left off last time talking about, as we mentioned, this movement of electrical activity is something that can be measured. The same way that if you have an electrician who comes to your house, they have a device that they can put on the wall and they can measure the movement of electrical activity to see if that electron is moving along the wire, to see where there's damage to a wire or where wires may be before they drill or something along those lines. And the same thing can occur with us by putting leads on the surface of the body. And again, this is an activity we would actually be doing in the classroom if we were in the classroom. You'd be measuring ECGs on each other. But luckily, we have some simulators that will allow us to examine that and the interactive physiology and things like that that we can look at. But we can measure that movement of electrical activity. And as we mentioned in the end of last class, we call that measurement an electrocardiogram. Now, again, it looks like a big squiggle when we look at this, but there are three main formations we are interested in. And let's actually go to the whiteboard for this. Again, you appreciate and understand how horrible my drawing skills are, but we will attempt, actually I'll cheat. We'll start with the straight line. And then we have three main deflections. The first deflection is called what?
The P wave?
Exactly. This is what is referred to as the P wave. Now, what is that a measure of?
The depolarization of the atrium?
Okay, so absolutely. This is a measure of the depolarization of the cells of the atrium. All right. And in general, one of the important things to remember about the ECG is the electrocardiogram is a measure of the change in the conditions of the cells. So it is a measure of the movement of change. Right? Again, let's think about that. How many cells here in this flat part are changing their state?
0.
Yeah, exactly. In the entire heart, 0 cells, no cells are changing a state. At this point right here, at the very begin of the deflection, right before it occurs, what percentage of cells of the atria are depolarized? 0, absolutely. So basically at this point right here, 100% of the atrial cells are at rest, at their resting membrane potential. And as you mentioned, 0% are depolarized. What about at the other end? Right at the other end, we have another flat part to our deflection. So let's go ahead and put our arrow here. At this point right here, what percentage of the atrial cells are depolarized? Exactly. At this point, 0% atrial cells are at, oops, that's not how you spell R, at the resting membrane potential, and 100% are depolarized. Notice we are not measuring the change in action potential. We're not measuring the fact that it's going from -70 to whatever it's going to, +30 millivolts or anything like that. What we are measuring is a current, yes, is the measuring of the movement of electrical activity in the cells. And if every single cell is depolarized, is there any change to be measured? No, and that's why the curve goes down. It's not like they start to be depolarized and they're all depolarized and they're all then repolarized back to rest. No, that is not what's happening. We are measuring the movement. We are measuring change. And at this point, there is no change. Anytime it is flat, and that's a good rule, anytime the curve is flat, there is no change. That is a good rule to remember. All right, so that is our P wave. I'm gonna have to cheat a little bit and I think sneak this over here a little bit more. so that I have room for our next deflection. What is our next deflection called?
QRS call.
T wave.
Yeah, the Q,
Oh.
which then leads into the R, which then leads into the S, and you're absolutely right. This is the QRX complex, QRS, pardon me. So we have this downward deflection and large upward deflection, and this is not drawn for scale. Whoops. A rapid downward deflection, and then an upward again. Each of these individual points are referred to as Q, are referred to as R, and as S. Notice this deflection is far more complicated than what we saw in the P wave. And as we mentioned, this is the QRS complex. And so just like we did for the P wave, tell me what is happening during this QRX complex. If the P wave is the depolarization of the cells of the atria, then what is the QRS complex?
Depolarization of the ventricles.
Okay, excellent. Anything else? Well, I'm asking the question, what should the obvious answer be?
Atrial repolarization occurs.
Exactly. Absolutely. We have this weird looking complex, not just a continuous wave like we saw with the P wave, because basically two different events are occurring. Cells in one part of the heart are going from an excited state back to rest, and that change is moving over the surface of the heart. But at the same time, as we know, that signal has to spread from the atrioventricular node down to the apex and up the walls of the ventricle and those Purkinje fibers to depolarize the ventricles as well. And so these two events occurring at the same time give us this complex wave signature that we call the QRS complex. And then notice again, we hit a flat point. And so what are the state of the cells in this flat part?
Ventricle depolarization is done.
Okay, so what percentage of our ventricular cells are depolarized?
100.
Exactly. 100% of ventricular cells are depolarized. Anything else? What percent of our atrial cells are depolarized?
0.
Right, they're all at the resting membrane potential. Excellent. Again, we are at this state where not that all cells are at rest or all cells are excited, but all cells are in a state of no change. Now, based on that, what do you think the function that is occurring, or the cause, or what the final deflection? What is our final deflection?
T wave.
T wave. What are the event or events that are occurring during the T wave?
Repolarization of the ventricle.
Excellent. Now let's see, if the depolarization of the P wave was an upward curve, then that means the T wave is going to be a downward curve, correct?
No.
Why not? It went up because our atrial cells got positive. Our ventricle cells are getting negative. So shouldn't our deflection go down?
I had the same question going over the homework.
Then there must not be an answer. If you and I can't figure it out between the two of us, then there must not be a good answer for it. Except there is. What are we measuring?
Change.
Change. Not membrane potential, not direction. We are measuring change. So how much change is taking place at this point right here? More than zero, but a lot or a little?
A little.
You're right. Whereas here, how much change is taking place?
A lot or
A lot.
more.
Maximum.
Right. Again, I like using very simple, very absolutely incorrect numbers because it makes it easy to understand. Let's say the entire ventricle only contained 10 cells. All right. So then if you think about what would be happening, when the first cell depolarized, we would get a little bit of a signal. Because of gap junctions, it would spread to 2 more. And those 2 would spread to 4 more. At this point, how many cells of my ventricle have been excited?
About half.
More than half. We started with 1, then we excited 2, then we excited 4. How many cells are there left to excite?
None.
Well, there were
3.
10 total. So how many are left? What's
3.
7? What's 10 minus 7?
3.
3. Again, I'm using easy numbers here to make it easy. Absolutely. So then that change spreads to 2, and 2 more get excited. And then there's only 1 left to get excited. And then suddenly they're all excited. Remember, these deflections are not a measure of the charge of the current. They're a measure of the change. So the bigger the deflection, the more change that is taking place. And of course, as we just finished talking about at the beginning of this, 100% of the ventricular cells are depolarized. And at the end of this, what percentage of our ventricular cells are depolarized?
0.
0%. Instead, they're all at the resting membrane potential. And all the cells are now back at the resting membrane potential. So if you think about it, that's exactly where we begun. And then the whole process starts anew.
Professor,
Yes.
what would happen if you got to the T wave and then the T wave, instead of going above the isometric line, went under it?
Then you put the leads on wrong.
Oh, okay.
Yeah, again, it's not a measure of voltage. It is a measure of change. Now you get this weird QRS complex because you have 2 different changes going in 2 different directions, and that's what causes this complex middle wave. But notice when we're just measuring change, doesn't matter if it's in the atria, doesn't matter if it's in the ventricle, doesn't matter if it's a positive change, doesn't matter if it's a negative change. In both, we see very smooth upward curves because what we're measuring isn't the voltage, isn't the direction, it is the change. It's a measure of the change. All right, we can,
So,
yes.
Sorry, I had a question. So the points at Q and S that are below the resting membrane potential, is that caused by the repolarization of the atrium?
In part. In fact, I was going to talk about this as we go next, but you bring up an excellent point. Yes, there is obviously a little bit more to this, but one of the things that I will tell you right off the bat, this Q deflection is actually the point where our electrical signal reaches the apex of the heart. So basically, this portion right here, basically what would be the PQ segment, is the portion where it is going through the atrioventricular node and the atrioventricular bundle and bundle branches. All right, so again, we have a basic understanding of what is going on in these individual deflections. But let's look more specifically and again, talk about this as we discuss it. Again, as we mentioned, the P wave is the spread of the electrical signal from the SA node across the surface of the atria, depolarizing the cells. Once, whoops, wrong button. Once the entire, and I'll cheat and draw it for myself. Once the entire atria is depolarized, why doesn't the signal instantly spread to the ventricles? Why do we have this flat part right here?
That's the delay of the atrioventricular node.
Exactly. So notice what happens when we hit that flat part. There is absolutely no change going on in the atria. 100% of the atrial cells are excited. But remember, as we talked about, that atrioventricular node has tiny, I don't like that. It has tiny, thin cells that slow it down. So this segment, and again, I should make a point of emphasizing this, when we're dissecting the components of this wave, there are segments and there are intervals. What's the difference between a segment and an interval?
Is the interval the deflection point?
Close. You got the right idea. Interval, and the way I remember it, I for interval, I for includes. It includes the wave. Whereas segments are between the waves. So notice this PQ segment is a measure of actually how long that delay in the AV node is. From that delay, the signal then spreads down the bundle branch, the bundle of His, down the bundle branches to the apex. And as I mentioned, when we reach that Q point is when the signal reaches the apex. It then spreads up the ventricles, depolarizing the ventricles. At the same time, our atria are repolarizing. So we have the repolarization of the atria. At the same time, we have the spreading of the depolarization along the ventricle. And that gives us our QRS complex. And again, brings us to another flat point, another point where no change is taking place. And that point where no change is taking place would be called what? How would we identify this component of our ECG?
A segment.
Yeah, but what would the segment be?
Is it the ST segment?
Exactly, the ST segment, absolutely. This SC segment, notice, is the period of time where the atria are fully at rest, back at the resting membrane potential, and the entire ventricles are excited. This period of time gives us an indication of, notice I said indication, it infers how strong and long the contraction is. The longer the ST segment, the more powerful the contraction of the heart, the longer the contraction of the heart. Because the longer these cells stay depolarized, the more they're going to contract. And then, as we mentioned, that final deflection is the measure of the repolarization of the ventricles, starting from 0% all the way till 100% are repolarized. At which point, every single cell in the heart is back at its resting membrane potential. and there is no more movement taking place until another action potential is produced by our SA node. And once that new action potential is produced, it spreads and the whole process continues again. Questions on this?
I have a question.
Yes.
So segments are between the waves and intervals are, what was the intervals?
Include the waves.
Include the waves, okay.
Right, here, let's take a look at this. Notice here, for instance, the PQ interval is from the very beginning of the P wave to the beginning of the Q wave. It includes the P wave. Whereas, as we mentioned, the PQ segment is the period between the waves. So notice the ST segment is the period between, whereas, for instance, as you see here, the QT interval includes the waves. So intervals include, that is how I remember it. That's the cheat that I use, whereas the segments are the pieces in between. Now, these, obviously, we can mix and match them however we want, but there is some significance to them. For instance, the PQ interval is an important interval because remember, as I mentioned, Q is the point when our electrical signal reaches the apex and is about to spread up the ventricle. The beginning of P is obviously when the first action potential is produced in that SA node. So notice the PQ interval is basically a measure of the time from the beginning of when the atria gets excited to the beginning of when the ventricle gets excited. Does that make sense? I mention this because if you're actually in a medical environment, often what they will actually measure is the PR interval. Why would you measure the PR interval instead of the PQ interval? Well, either you haven't spent a lot of time in a medical environment or you're embarrassed to give the right answer. I want to give it a gander. Why might, when you're looking at an ECG on the chart, you want to identify the PR interval instead of the PQ interval?
Because since the R has to do with ventricular depolarization, then we want to see how it goes through the entire system first.
That is an excellent answer and a thoughtful answer, but I think Samuel's actually got it right. It's easier. What's easier to see, Q or R? Has anybody actually seen an actual ECG? Do they look all beautiful and all spread out like this one we have on the page right here is? Not always.
No, not always.
Yeah, exactly. So the R is way easier to see. And is there a huge difference in time between the Q and the R?
No.
No, we're talking about hundredths of a second. So while it's may not be as precise, it's a heck of a lot easier. And so it gives you a very nice general idea, and it's much, much easier to identify. So yeah, you absolutely hit it you hit it on the head. It is because it is easier to see. And that's the only reason they would do that. For the same token, as we mentioned, I think I have it on here, so maybe we'll wait till I talk about it. ST segment, as I just mentioned, that gives us an estimation of how long the muscle of the ventricle is excited for, and that can give us an indication of how strong or how long the contraction is going to be. QT interval, from when the very first cell of the ventricle is excited to when the very last cell of the ventricle is excited. Actually, I guess they're saying that's the end of T. So there you go. I'll put it there. So all of these are examples. And then as I was about to mention, I thought I had it here, but bear not. What is the RR interval?
Is that the complete heartbeat?
Yeah, that is the exact amount of time it takes for one full complete heartbeat. Now, wouldn't it be the same if we did PP or QQ or SS or TT? Yes.
Yeah.
So most of the time when you're in the medical setting, why do they do RR?
The easiest to see.
There you go, because R is the easiest to see. There you go. It really is just that simple.
Would it also be easier, or like, would you have more of a correct reading because there's a bigger difference? It would be easier to read versus like,
Sure, definitely going from the peak of P to the peak of the second P, or from the peak of Q to the peak of the other Q, it's a lot more subjective. Absolutely. So because R is such a large deflection, it is a lot easier to find the top of it because it's so big and so rapid. So yeah, you can probably be a little bit more precise in your measurement that way as well. Sure. But again, don't devalue the fact that something is easier. Easier is not necessarily a bad thing. All right. Again, of course, this is how this works properly. There are, again, you've got the interactive physiology, which talks about some examples of some things, heart block and other activities that we will talk about. And then, of course, this works because we have, as we've talked about, this wave-like fashion by which the SA node fires first, and that spreads through the cardiac conduction system. But remember, as we also talked about, every single cell in the cardiac conduction system is capable of producing its own action potential. So if instead of going to the normal sequential, if suddenly one of the cells in the ventricle becomes stimulated and fire, it's going to spread its activity, and others may become spontaneously active and spread that activity. And suddenly everything is out of sync. And if you were to measure someone when we were in that state, a state of fibrillation, which is what we call a very rapid irregular contraction of the muscle fibers of the heart from that lack of synchrony in the cardiac conduction system, you get these very funky looking waves like this one we see here. And when you talk about to cardiovascular surgeons who are actually doing surgery on a heart, when something like this occurs, they say the heart looks like this wriggly bag of worms, because all the different parts of the heart muscle are firing and contracting at all these different times. And how do you resolve this? If someone is in ventricular fibrillation, how do you resolve it? Well, how do you try to resolve it?
Use a defibrillator.
Okay, and what does that do?
Restarts the pacemaker.
Okay, a little bit more than that. Again, that is a reasonable explanation, but I think now we have enough knowledge where we can be more specific. What do you think that fibrillator actually does?
It sends an electrical signal to the heart, trying to reset it.
Absolutely. What you do, right? Clear, thump. And the point of that is to stimulate all of the cardiac conductive cells at once. Because if we can get every single one of those cells to be excited at the same time, then they're also going to repolarize at the same time. And once they're all repolarized at the same time, shouldn't the SA node, which has the highest spontaneous rate, be the first one that's going to fire its action potential after they've all recovered and then reestablish our normal wave that we had before? Yeah, that's the goal of that. The point of that is to get all the cells of the heart excited at the same time, get them all into that relative refractory period, let them all depolarize at the same time. And then as long as the SA node is intact and functioning properly, it should be able to fire the first action potential, and that action potential would spread down the cardiac conduction system the way it's supposed to, and we can reestablish a normal heart rate. So that's the whole point of that defibrillation. Basically, it's to stimulate the entire heart at once to try to, as you guys were right, absolutely correct. We want to reestablish the normal rhythm. We want to stimulate the SA node to be able to fire and start the process. But the way we're able to do that is by getting the entire heart cells excited, to let them all recover at the same time, and then hopefully begin that normal spontaneous rate. All right. Questions on that?
So what are conditions where that wouldn't work?
There are several, but here's the two simplest that I could think of. If there is something wrong with the SA node where it's not able to be rapidly spontaneous, then again, other cells would become spontaneous first. And so you wouldn't be able to reestablish a normal rhythm that way. Also, if there was some type of chemical or mechanical irritation to the ventricle cells that were causing those ventricular cells to fire their action potentials more rapidly than normal, then they could outcompete the SA node to fire their action potential first. And again, you would still have a disruptive system. So there are numerous things that could cause it, but those are probably the two simplest. All right. One last major important point I want to emphasize. So for instance, and I'll use a green arrow here to emphasize it, even though we've talked about it already. At this point right here, what % of our atrial cells are depolarized?
0%.
0. How many are depolarized right here?
All
100.
of them.
All of them, 100%. How many of the ventricular cells are depolarized right here?
100%.
Right. How many of our ventricular cells are depolarized right here?
0%.
Excellent. Notice we can, from this, say some pretty specific information about what's going on in the heart. As I mentioned, this Q deflection is when the electrical signal reaches the apex of the heart and all these types of things. However, if I were to try to draw a blue box, let's say I drew a blue box, and I wanted to move that blue box so that it showed and represented the time where the atria was contracting, where would I put this square?
Over the
Is
P wave?
this the period of time where the atria is contracting?
No, over the P wave.
Like that?
No, between P and Q, that segment,
That right there?
not including the P wave.
Not including the
So-
P wave. There. So here. I think Al has got it. This is not a measure. One of the most important things you can remember about the ECG is the ECG is not a measure of mechanical activity. It's impossible for us to put a square here over the part where the atria is contracting because this doesn't show us. Now, there are some hints we could use. So let's start easy. I'll put a line. Obviously, is there any way the atria could be contracting before this line I just drew?
No.
But when the very first cell becomes depolarized, is now the atria suddenly contracting? Well, let's think back to what we learned about with a twitch. The second we stimulate a contractile cell, is it instantly producing tension? No,
No.
remember the twitch has 3 phases. And what's the first phase of a twitch?
Latent phase.
A latent phase. And how much tension is produced during the latent phase?
None.
None,
None.
0. And even if that first cell was instantly producing tension, which it isn't, is one cell producing tension by enough to be considered a contraction of the atria?
No.
No. So what percentage of the cells have to be excited? How long is their latent period? Where does this begin, right? We can't put a measure onto where it actually is. We know it's definitely not before this. Firing before this, but we don't really know where after. And we don't even necessarily know where it's going to stop. Remember, this QR complex is the depolarization. We know at this point, I got to move this now. At this point right here, now 100% of our atrial cells are repolarized. And so if 100% are repolarized, right, is there still a little bit of tension necessarily in that muscle? What do you think? Potentially there could be, even as the cells are relaxing. As we know, it takes time to pump the calcium out. So even once the resting membrane potential goes back to, resting, as we know, there's a little bit of a delay. We have to pump that calcium out or put it back in the sarcoplasmic reticulum. We have to stop producing the tension. So we know it's going to be somewhere probably around here, but we don't know exactly where. And so that's the point, the last point I really want to emphasize. We obviously know that when the atria are excited, they are going to contract. So we know one event leads to the other, right? We can infer what is going to occur. But can we measure it using an EKG?
No.
No. And so that's the other big point I want to make about this. Obviously, when atrial cells get stimulated, they're going to contract. When they stop being stimulated, when they go back to rest, they're going to relax. But this does not show that. This is not a measure of mechanical activity. This is a measure of change of electrical energy. All right. Questions on that? All right, excellent. I'll get off my soapbox about that then. Excellent. So, as we mentioned, our basic heart rate is intrinsic, right? Produced by the cardiac conduction system. But as we've already talked about and learned, it can be modified by the autonomic nervous system. Explain to me specifically how. I'll make it easier for you. How many branches of the autonomic nervous system are there? Two. What are they?
Sympathetic and parasympathetic.
Excellent. How does the sympathetic nervous system modify the basic heart rate? Excellent. It's going to increase the heart rate. How?
By pumping more sodium.
Excellent. How does it get more sodium into the conductive cell?
Because there are pumps on the cell. Or sorry, channels.
Excellent. Sam, what does it use to open those channels?
Norepinephrine.
Norepinephrine. Excellent. To, excuse me, open sodium channels. And why does opening those sodium channels increase heart rate?
It makes the cell positive faster, so it allows for more action, or excuse me, it allows for faster action potentials to be to occur.
Excellent, right? Absolutely. So it increases heart rate by using norepinephrine to open sodium channels on the conductive cells that bring them to threshold faster. So we get faster action potentials, we get an increased heart rate. Excellent. So conversely, tell me what happens with the parasympathetic nervous system.
It slows down the heart rate.
Excellent. So it decreases heart rate by using,
Acetylcholine.
excellent, acetylcholine. To do what?
To open the chloride channel.
On the conductive cell. And that brings the cell to threshold slower. And it slows the heart rate down. Excellent. So definitely our sympathetic nervous system. And remember also our sympathetic nervous system can also release adrenaline or epinephrine into the blood to do the same thing. And certainly when you're relaxing, your heart beats slower. When you're stressed, your heart beats faster. But something else happens when you're stressed. Not only does your heart beat faster, but what else happens?
Blood pressure increases.
True, because you're putting more blood into the blood vessels. Part of the reason for that is the heart is beating faster. But what other effect does it have on your heart? Not only does the heart beat faster, but what also does it do?
Beats stronger.
Yes. The question then becomes, how does it do this? How does it do this extra thing that the sympathetic nervous system doesn't? Does the heart beat weaker when you're in a rest and digest state? Or does it just beat slower?
Isn't it just slower?
It's just slower, absolutely. And the reason for this are the pathways. Let's take a look at this here. As I'm sure you remember from 430, the pathway of the parasympathetic nervous system from our central nervous system starts in the brainstem of the medulla oblongata. That comes out axons via the vagus nerve. That preganglionic axon goes all the way to ganglia that are right at the heart or inside of the wall of the heart. And then those postganglionic neurons, notice, innervate the SA node and the AV node. Releasing that acetylcholine, decreasing the rate that it reaches threshold, slowing the heart rate down. Conversely, our sympathetic nervous system, as we know, starts in the lateral gray horn of our spinal cord, out the ventral root to the spinal nerve, to the white ramus, where it's going to ascend, going to the heart, to either the middle or the inferior cervical trunk ganglion. Where it then synapses on our postganglionic cell. And then our sympathetic nerve travels out to the heart. But notice what happens when it gets to the heart. Not only does the sympathetic nervous system innervate the SA node and the AV node, releasing that sodium, making it beat faster, but notice our sympathetic nervous system also innervates the Purkinje fibers. And because it also innervates the Purkinje fibers, this is where it makes the heart beat stronger. So not only does it beat faster, because remember, as we talked about, faster isn't necessarily a more efficient pump. But if we can get it faster and stronger, then it's going to be able to pump out more blood more efficiently. And I think it was Jacob that said it. Remember also, this means that our sympathetic nervous system can directly affect blood pressure. Whereas because the parasympathetic doesn't innervate the Purkinje cells, fibers, doesn't innervate the ventricles, it is not going to have that same direct effect on blood pressure. So our sympathetic has a much greater effect on blood pressure than our parasympathetic does. Questions on this? I know I told my class, and hopefully your 430 teacher told you as well. Again, the stuff we did in 430 wasn't randomly pulled out of the hat. And of all the stuff we learned in 430, the two things that I said were going to be most important were our tissues, what we learned about the tissues, and what we learned about the autonomic nervous system. So hopefully you've retained that information.
I have a question.
If you did not, hold on, let me finish my, if you did not, then I strongly encourage you to go back to, I think it's chapter 14, 13, something like that, where it talks about the autonomic nervous system and read about these pathways. Yes, go ahead.
So when it comes to a heart transplant, what happens to these nerves, the innervation of the sympathetic and parasympathetic?
Nothing. They are so the short answer is in depending on the condition of the heart. In some cases, they will just do a piggyback surgery. They'll put an additional heart in there to assist the original heart. If there's some serious damage with the heart and the heart has to be removed, when you have that new heart put in, there's no way to reconnect these wires. So basically, when you have a heart transplant, you also have a pacemaker, and that pacemaker is going to be what is solely responsible for modifying the heart rate. As we know, the heart, if it's a healthy heart, has its own autorhythmic cells that are intrinsic and can fire at its own rate, but you will still need an artificial pacemaker to be able to moderate it and maintain it, and to make sure that it is working at the appropriate levels. Yeah, so there's no way to, you can, in fact, when you speak with cardiovascular surgeons, they refer to themselves as plumbers and not electricians, right? They can connect the pipes, but they can't connect the wiring.
So would somebody with a heart transplant, like not, if they were scared or anxious, their heart rate wouldn't naturally change? It would stay the same?
Great question. So what I would say to that is that while certainly the direct neural input from the sympathetic nervous system wouldn't be there, but remember, when you get scared, you're still releasing adrenaline into the blood. And
Right,
that adrenaline would affect the heart. So yes, so vigorously exercising, or you got scared or something like that, yes, that could, by the effect of adrenaline in the blood, you could still get the heart to beat faster and stronger.
Thank you.
Yep. Excellent. Great question. Any others? All right, spectacular. Where are we on time? It's a teeny bit early, but this is a good natural stopping point. So let's do this first, and then we will take our break. All right. We have talked a lot about all of the electrical events of the heart, the cardiac conduction system, how we can modify it. But we still need to talk about the mechanical events. And the description of the mechanical events that are caused by that movement of electrical activity are what we call the cardiac cycle. Now, of course, what's the key word in that phrase?
Cycle?
Cycle, because what does cycle mean?
It repeats itself?
Yeah, it is a continuous process, like a wheel that goes round and around and around. The cardiac cycle is the exact same way. And your book's got this pretty picture that I'll show you in just a second that measures this. But as we know, these mechanical events follow, or we could also say are caused by, the electrical events. But remember, they are not measured by the ECG. All right, obviously we know when the atria gets depolarized, they're going to lead to a contraction, but the ECG doesn't measure that. And of course, the point of the cardiac cycle is to pump blood throughout our body. And of course, as we know, all movement of blood, in fact, everything in the whole wide universe, is controlled by what major process? What is the most important force in the entire universe?
Pressure?
Yes,
Pressure.
I love love. I
And then
love
love.
money.
Money.
Gravity's a good one. Pressure, absolutely. Pressure is what truly makes the world go round. Pressure changes. So we change the volume of our chambers. And as we change the volume, the pressure drives the blood where we want it to go. So that contraction and relaxation of the chambers decreases volume. And of course, when you decrease volume, what effect does that have on pressure?
Increases pressure.
Increases pressure. And then when you relax the chamber, we increase the volume. And of course, when the volume increases, what effect does that have on pressure? There you go, decreases pressure. Spectacular, excellent. So these changes in the shape, changes in the volume of our chambers, change the pressure, and that pressure change moves the blood. And here is the pretty picture that I will leave you with going into our first break, where we will talk about all of these events of the cycle from start to finish to where it starts back again. All right, questions on this? All right, let's go ahead and take our first break. Looks like, what time is it? 1:07. All right, so 15 minutes would be 1:22. So we will come back at 1:22, and at 1:22, we'll pick up the lecture from here. Any questions? All right, see you in 15 minutes. All righty. Let's go ahead and get started. We are now going to talk about our first really big major physiological process here. And so as we do this, what I often like to do with big, more complicated physiological processes is go through them twice. For this first time, I like to do the drawing on the board, or the whiteboard in this case here, and we'll go through it that way. And for this one, I strongly encourage you to just put your pens and pencils down, just watch, listen, think about what it is that we're doing. What I find is if everybody's furiously trying to write down the words that are coming out of my mouth, then you're not paying any attention to the words that are coming out of my mouth. So for this first one, you just sit back, watch, think, listen. Then after we go through this process once here on the board, then we'll go through it with all the pretty pictures and all the pretty words, and you can continue to write till your heart's content at that side. All right. So with that in mind, let's go ahead and get started with our discussion of the cardiac cycle. And of course, we need a starting point, and that starting point cycle, it's a continuous process, but a good starting point from this will be to start from the point where the entire heart, I think we can do this, make this work and give us some room to play. So again, we'll draw my simple schematic of the heart. We'll put all the detail in this one. We may not be as detailed in all the rest, but if we have the detail in the first one to refer back to, it will help us. All right, and let's write small here. Obviously, this is the right side over here, so I'll just put a very simple right atrium and right ventricle, and then left atrium, left ventricle. That works. And remind me again of these blood vessels. What are the blood vessels that feed into the right atrium?
Superior and inferior vena cava.
Excellent. And what are the blood vessels that feed into the left atria?
Pulmonary veins.
Excellent. What blood vessel receives blood from the right ventricle?
Pulmonary trunk.
Yeah.
And Professor, doesn't the coronary sinus also go into the right atria?
Yes, absolutely. And of course, there are 4 pulmonary veins. But again, for this purpose, especially since we're just talking about the systemic and pulmonary circulations, we don't have to worry about that too much. But yes, you're absolutely correct. It would be correct to put that there as well.
Right.
And what is the blood vessel that receives the blood directly from the left ventricle?
Aorta,
Although we want to be a little more precise.
ascending aorta.
Excellent. All right, so this is our starting point. 2 more things we need to add to this. At this starting point, and again, in this continuous cycle, we have the conditions of the aorta. And are the state of our aorta, are they depolarized or are they resting at the beginning point?
Resting.
Resting, absolutely. So if they're at the resting membrane potential, is the state of them in a state of contraction or a state of the relaxation?
Relaxation.
Relaxation, absolutely. And we have fancy terms that we use for when we're talking about a chamber of the heart being in a state of relaxation or a state of contraction. What are those fancy terms we use for that?
Diastole and systole.
Yeah, absolutely. So systolic and diastolic, or diastole and systole. Which one means a state of relaxation?
Diastole.
Diastole.
Absolutely. So our atria is in a state of diastole, so it's diastolic. And what about our ventricle? Is it diastolic or is it systolic?
Systolic.
Diastolic.
It's also excellent. So when the heart is quote unquote at rest, which I think I may have to cheat and move this over here. Excellent. So both are in a state of diastole. And we also want to think not just in terms of what's going on with the chambers, or the chambers contracting or the chambers relaxing, but we also want to think of what's going on in terms of the valves. Valves come in 2 flavors. What are the 2 types of valves?
Atrioventricular and semilunar.
Excellent. And actually, you know what? Now that I've done this, I want to change this. Hold on a second. Excellent. So we have our atrioventricular valves, which are between the atria and the ventricles. And what is their state when both chambers are diastolic? Does anybody know?
They're at rest. They're open.
Excellent. So our atrioventricular valves are open. And what is the state of our semilunar valves when everything's at rest?
Closed.
Closed. Excellent. So our atrioventricular valves are open and our semilunar valves are closed. So this is our starting point. Again, our entire heart is at rest at this point. And so if you think about what's happening, as we know, blood is coming back to the right atrium from the superior vena cava, inferior vena cava, and the coronary sinus. Blood is coming back from the pulmonary veins into the left atrium. And as these fill with blood, and the fact that the atrioventricular valves are open, and the fact that the atria are superior to the ventricles, is the blood just going to stay in the atria?
No.
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 So what's going to happen is that blood is going to continue to flow down into the ventricles. Notice this is not requiring any type of ATP. What we're actually getting here is a passive filling of the ventricles. So at this point, we have this passive filling of the ventricles as the blood is coming back from the body, as the blood is coming back from the lungs, it is entering into the atria, filling the atria, which we saw were tiny little things. And since the AV valves are open and the ventricles are beneath the atria and the blood is constantly coming in, that pressure pushes it into the ventricles and we get this passive filling of the ventricles. All right. Questions on that? All right. While I am redrawing my heart here, someone tell me electrically what the first event that occurred in our cardiac conduction system is.
Depolarization of the atrium.
Excellent. Depolarization. And where did that occur?
Right.
I'm sorry, where?
Right atrium.
Okay, but what is the structure? What's the although remember, we want to be careful with abbreviations. So yes, SA note is correct, but that's kind of a spelling error. So what would be the appropriate way of describing it?
Sinoatrial.
The sinoatrial node. So excellent. The sinoatrial node becomes active and we get the spread of an electrical signal across the atria. And when that occurs, what is going to happen to our atria?
It's gonna contract.
Absolutely. So as a result of that spread of electrical signal, we get a contraction of the atria. Now, when this occurs, again, if we are thinking in terms of the conditions of what things are going on in our heart, now our atria are in a state of systole. It is systolic. But what about our ventricles? Are they changed?
No.
No, they're still diastolic. What about our AV valves? Are they still going to be open or closed?
Closed.
Well, but if the atria is contracting, isn't the pressure in the atria going up?
It's gonna be open.
Right. Yeah, our atria are systolic. That means there's an increase in pressure. And if there's an increase in pressure, that means blood wants to be there even less. So it's going to want to go into the ventricles. So our AV valves stay open. And is that going to change our semilunar valves at all? No, exactly. So our semilunar valves stay closed as a result of this. Absolutely. So again, there's no change in our valve condition. but now we are getting a more active, a more active pumping of the blood. Actually, I don't like that. We're getting an active pumping of the blood into the ventricle. And in fact, that's what we call this stage. This is the active filling of the ventricles. Now, just out of curiosity, which of these two processes, the active filling or the passive filling, do you think moves more blood into the ventricles?
Passive.
Yeah, in fact, about 80% of the total volume that we're going to have in our ventricle is passively put into that ventricle just by it flowing down. So that means only about 20% is moved with the force of that ATP. So notice, if you think about it, the very first thing that occurs is this atrial filling that occurs in two steps: passive and then active filling of the ventricles. So that ventricular filling is the first step of our cycle, and it occurs in two steps. First, a passive filling of the ventricle, and then an active filling of the ventricle. Questions on that? All right, what's going to happen next electrically?
There's a delay at the atrioventricular node.
True, there is a delay at the atrioventricular node, and then what happens?
It travels down the bundle to the Purkinje fibers.
Excellent, and then what happens?
The ventricles contract.
Well, first it spreads up the ventricles, up those Purkinje fibers, and then you're right. Then what's going to happen is that the ventricles are going to contract. Anything else happening at that time as well?
Atrium gets repolarized.
Exactly, absolutely, excellent. So notice, as that electrical signal spreads, we start to see some big changes that are taking place in our heart. Our atria are going to enter diastole. Small. That's too small. Are going to enter diastole, and our ventricle is going to just begin systole. Just going to start to become systolic. Now, as we know, when a muscle begins to contract, is it right away producing massive amounts of pressure? No, it takes time for it to build. So it is still at a low pressure at this point. However, as it turns out, a low pressure is still going to be enough to cause our atrioventricular valves to close. So what's going to start to happen is we get this little bit of pressure from the ventricle starting to contract. And when that occurs, that causes our AV valves to slam shut. And if I happen to be resting my head on your chest when this occurred, how would I know that the AV valves closed?
You would hear
The first sound.
Yeah. We'd get that lub sound as a result of it. However, if my ventricle is only producing a little amount of pressure, do you think that's enough to push open those semilunar valve doors with all the blood from your lungs and all the blood from your body on the other side of those doors?
No.
No. So notice what happens at this point in this period of time is that both the AV valves and the semilunar valves are closed. Notice with this being the case, there can be no change in the level of blood in the ventricle. In fact, our ventricle has reached its max volume. So however much blood we've been able to get into here, this is the most we're going to be able to get. This is the max volume that we're going to have in here. And because this happened while the ventricle was relaxed, we call this, excuse me, the end diastolic volume, which once you've written out once, you can abbreviate EDV. All right, you with me so far?
Yep.
Okay, complete silence means that, yes, I understand this perfectly. Please talk faster. All right, excellent. So much like this can of soda, there is now a set volume in it and the top is sealed, so it is completely closed. Now, I'm only pushing a little bit of pressure on this can, but as I start to squeeze it more and more and more, what's going to happen?
The pressure increases.
Right, the pressure is increasing, but am I going to be able to change how much soda is inside of this can?
No.
Well, I'm not going to be able to pop the top like Popeye, have the spinach jump out, land into my mouth, chew it up, save olive oil and everything that goes along with that. Am I going to be able to change the volume of soda that's inside of this no matter how hard I squeeze? No. And that's exactly what's happening here. What's happening here is that, whoops, no, hold on, I want that to stay red. What's happening here is that I'm getting an increase in the pressure of the ventricle, but is the volume in the ventricle changing?
No.
No. And so I have a very fancy name for this period of time where there is a continued increase in pressure in the ventricle, but the volume stays the same. And the fancy name we give for this is an ISO. What does ISO mean?
The same.
Same. Volumetric. So notice the volume doesn't change, but the pressure is increasing. This is an isovolumetric contraction. All right. You with me so far? All right, excellent. Now, we have already established that I am not strong enough to be able to bust open this can just by squeezing it. But what if we took somebody who was more fit, more capable, right, stronger than I am, right? Let's say that, for instance, I don't know, Jacob, because he's on camera, who is much more manly than I am, was to squeeze that can. Would he be able to squeeze it? And if you were able, let's say if you're able to produce enough pressure, could you pop the top on that can and have soda come out? If
Yes.
someone was strong enough?
Yeah.
Yeah, absolutely. So, and the same thing happens here. The pressure in the ventricle continues to increase as the ventricle squeezes more and more and more, and the volume gets smaller and smaller and smaller. The pressure is going to continue to go up and up and up until eventually the pressure inside the ventricle is greater than the pressure inside the arteries. And when the pressure inside the ventricle gets to become greater than the pressure inside the arteries, what's going to happen?
The semilunar valves are going to open.
Exactly. So our AV valves are still closed. Again, now our atria is full on diastolic. Our ventricle is full on systolic, producing a very high pressure. And because of that, while certainly it doesn't open the AV valves, now our semilunar valves are forced open. Because the pressure inside of here, because of the huge force of this contraction that it is producing, massive, nope, that should be green. Massive force that it is producing. That massive force is now able to force our semilunar valves open. Oops. And as we force these valves open, the blood is ejected from the heart into the arteries. And that's what we call this stage. This stage is ventricular ejection. Where the force of the ventricle is great enough to overcome the pressure in the arteries, and it forces the blood out. Questions on that? All right, now, does the heart continue, does the ventricle continue to contract forever?
No.
No, absolutely not. So eventually it's going to start to relax. And as we know, does the pressure instantly go back to zero? Does it completely relax instantaneously and suddenly there's no more pressure in it?
No.
No, but it is going to start to relax. And as it starts to relax, the pressure is going to go down. Again, as we've talked about, pressure is what makes the world go round. Here, the pressure in the ventricle is greater than the pressure in the arteries. Because it is greater than the pressure in the arteries, we're able to force that blood out. But now the ventricle starts to relax. So again, as we know, our atria is fully diastolic. Now our ventricle is entering diastole. And so we get a decrease in pressure. Of course, as we know, the AV valves are still closed. Let me finish the rest of my drawing here. That there, that there, that there, that there, 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 and there. Our AV valves are still in their closed state. But we had just crammed a massive amount of blood into these arteries. And when you force blood into arteries, what do you do to the pressure?
Decrease.
Increase.
It increases, absolutely. It increases the pressure. And now the ventricles are starting to relax. And as they're starting to relax, that blood's not going to want to stay there, and it's going to want to try to come back into the heart. All right, the same way that it tried to leave here. And as it tried to leave here, it slammed the AV valves closed. So as this blood tries to go back into the ventricle, guess what happens?
Closes the semilunar valve.
Exactly, our semilunar valves are going to close.
In the process of closing, is there some blood that moves back into the ventricles?
No. Maybe a small amount, but not a significant amount. No. No. Sky is blue. No. Does not. So they close. And of course, when they close, how would you know that if you were resting your head against somebody's chest? You get the dub sound. Absolutely. The dub of our love dub. Absolutely. Notice at this point, again, two major things have occurred. For starters, do you think we've gotten all of the blood out of the heart that was in there? Did we just wring that ventricle dry?
No.
No, there is going to be some blood left inside of the ventricles. So notice, once again, we've reached a state where all four valves have closed. And because all four valves have closed, we have now reached the state where there is no change in the level of the blood in the ventricle. And so at this point, we have reached its minimal volume. And we call that minimum volume the end systolic volume. Which once you've written out once, you can abbreviate ESV. So just out of curiosity, if you wanted to figure out how much blood was actually pumped out of the heart, what would you do?
Measure the amount of blood in the ventricles before the semilunar valves are open and then after.
Okay, so don't we have those two values, an end diastolic volume and an end systolic volume?
So you find
Yes.
a difference.
So what would you do?
Find the difference.
Right, absolutely. If I told you the end systolic volume was 120, and the end diastolic volume was 120, and the end systolic volume was 20, how much blood was moved?
100.
Yeah, there you go. See how easy that is? Exactly. We can figure out exactly how much is moved that way. Now, notice once again, the heart is relaxing. So we are getting a decrease in the pressure of the ventricle. But is the volume in the ventricle changing?
No.
Stays the same. So if when we increase the pressure in the ventricle, but the volume stayed the same, we called it an isovolumetric contraction. What do you think we call it when the volume of the ventricle stays the same, but the ventricle's pressure is going down?
Isovolumetric relaxation.
Perfect. Questions on that? Alrighty. I've run out of room to write, so I will cheat and I don't know where I'm gonna put this. Hold on, let me see. I move this up and that up, that, and I can get a teeny bit of room down here. All right. What is the state of my atria at this point?
Diastolic.
What is the state of my ventricle now at this point?
Diastolic.
Diastolic.
Excellent. What is the state of my semilunar valve?
Closed.
Closed.
Closed. Excellent. Perfect. So we've got all of those things that we know. This is closed. This is closed. But notice what we haven't been talking about is what's been going on in the atria for all of these past 4 steps or 3 steps. What has been happening in our atria during these last few steps?
Has it started passive filling again?
It hasn't just started, it's been passively filling the whole time. Notice again, there are no valves stopping blood for coming back. So this whole time, all these events have been occurring inside of our ventricles. We have slowly been filling our atria with blood. First a little bit, then a little bit more, and then a little bit more. Again, it's not a massive flow and it's not a high pressure, but we are slowly filling this area with blood as that blood comes in. And as that blood comes in, there is some minor pressure as a result of that. And eventually, when the pressure in the atria is greater than the pressure in the ventricle. Whoops, why did that stop writing? What's going to happen?
AV valves open.
There you go. Now, notice, did these AV valves open because my atria contracted? No, they opened just because there was a buildup of pressure. And because there was a buildup of pressure and that blood was filling it, that blood now forces its way into the ventricle. And notice, lo and behold, what's going on here. Suddenly, we are getting a passive filling of the ventricle. And why does that sound familiar?
It's the first step.
First step.
Because we're right back where we started and our cycle continues. And that, just that simply, is our cardiac cycle.
Can you save this graphic?
Yes, I can.
Thank you.
All righty. We've done it once on the board. Let's look at all the pretty pictures, all the pretty words, and go through this again. Again, technically this is a cycle. We could start this cycle at any point. But the easiest place to start it is this point where the entire heart is at rest. And so if we start with the entire heart at rest, notice here we have a more accurate representation of the heart. But if you notice, all the things that I drew are all still accurate and all still here. Notice we have, let's use green so it'll stand out at a line. Our AV valves are open. Our semilunar valves are closed. Our atria and our ventricles are at rest. And blood is flowing back to the atria. Where it then continues on down into the ventricle with nothing but the volume pressure of the blood causing this change. The heart is not using any ATP for this, right? Heart is at rest. AV valves are in what state? Open.
Open.
And we are getting this passive filling of the ventricle. Again, no ATP is being used. So the first thing that is happening is this passive filling. And as we mentioned, the majority of the blood, something close to 80% of the blood we're going to get into our ventricle, occurs during this passive filling. But 80% isn't 100. How do we get the rest of the blood into the ventricles?
Contraction of the atria.
We contract the atria, absolutely. So we started with that atrial filling, passively filling the ventricle. But now, as you can see, our atria are contracting, moving the remaining blood into the ventricle. And remember, at the end of this process, again, notice there are 2 points I want to make. This does not close the AV valves. The contraction of the atria does not close the AV valves. But when they do close, we are going to reach our maximal volume of blood in the ventricle. And what do we call that maximal volume of blood in the ventricle? If you're not sure, you can just read it off the slide.
And diastolic volume.
There you go. It's the end diastolic volume. All right. Questions on that?
Sorry, Professor, could you just repeat what you just said with that, but when they do close?
When the atrioventricular valves do finally close, then we have gotten the most blood we can into the ventricle. There's no way to get any more blood into the ventricle. And so our ventricle is at its maximal volume. And that maximal volume of the ventricle is the end diastolic volume. So like I said, the passive filling gets 80% of that volume in there, and the ventricular filling gets the remaining 20% in there.
Thank you.
Yep.
And then it's the pressure of that volume that closes
No.
the AV valves.
Great question. I'm so glad you asked that. No, it is the pressure of the ventricle that closes the valve, but not from us putting the blood in there, but from the ventricle starting to contract.
Okay, thank you.
Right? Yes. So great. This does not occur until the ventricle starts to contract. But as soon as it does start to contract, that's when, so notice we're getting that start of the contraction of the ventricle. At the beginning, when the pressure is small, it doesn't take a lot to close the AV valves. So when the pressure is small, it is great enough to close the AV valves, but not strong enough to open the semilunar valves. And so what happens is we reach this brief period of time known as the isovolumetric contraction. All of our valves are closed, but the ventricle is continuing to contract. And because the ventricle continues to contract, we get an increase in pressure, but no change in volume. And that is why it is an isovolumetric. The volume does not change, but the pressure is increasing. It's an isovolumetric contraction. Now, this period of time doesn't last very long because the pressure of the ventricle continues to get greater and greater and greater and greater until finally the pressure in the ventricle is strong enough to force those semilunar valves open. And once the pressure inside the ventricle is greater than the pressure in the arteries, blood is forced out of the ventricle into the arteries. In that process, we call ventricular ejection. Now, as we talked about, are we going to be able to get all of the blood out of the ventricle?
No.
No, there is going to be some blood left behind. And that little bit of blood left behind, we call the end systolic volume. Now, that ventricle contracts for a good, long, strong contraction, powerful contraction, but it doesn't stay contracted forever. So it starts to relax. And again, as the ventricle starts to relax, the pressure goes down. And as the pressure goes down, now suddenly the pressure in the arteries is greater than the pressure in the ventricles, and that slams the semilunar valves closed. And we get our dub. Notice we weren't able to get rid of all the blood. There's still some left behind. And we call that the end systolic volume. At this point, as we've talked about, all 4 valves are closed. So even though our ventricles are relaxing and the pressure is going down, the volume stays the same.
And at this point, the AV valves and the SL valves, they're both closed?
Yep, all the valves are closed. Absolutely. So that's the point. That's how the volume stays the same. That's why this is an isovolumetric relaxation, because the volume doesn't change. If one of these valves are open, then their volume can change. Blood's either coming in the AV valves or leaving the semilunar valves. So the only way the volume can stay the same is if there's no way out. And so with all 4 valves closed, the volume stays the same as the pressure continues to decrease. But notice we haven't been talking about it, but notice that the pressure, the blood has been accumulating in the atria. And as soon as the pressure in the ventricle becomes less than the pressure in the atria, what's going to happen?
The AV valves will open.
The AV valves are open, and we will start our passive filling again. And then the whole cycle begins all over again. All righty, excellent. Questions on that?
So it never uses ATP, it just uses pressure.
Well, no, great question. The passive part doesn't use it. When the atria are contracting, we're using ATP. When the ventricles are contracting, we're using ATP. So when the chambers are actively contracting, that is when they're using ATP. But only when the muscle cells are contracting. So notice this picture is part of a great illustration you have in your textbook. Notice it shows us the states of the valves. AV valves are open during the passive and active filling, while the semilunar valves are closed. Then when the pressure begins, we get the closing of the atrioventricular valves. The aortic and semilunar valves stay closed. So notice that's our isovolumetric contraction. And this closing gives us our lub sound. Then as the pressure increases, we get an opening of our semilunar valves until the point where the pressure gets low enough inside of them that they close again, and we get our dub sound. And notice here, both sets of valves are closed. That's our isovolumetric relaxation, until the pressure in the ventricle gets so low that the semilunar valves, a big part of the AV valves open again, and it starts our passive filling, and then the active filling, and the process continues. Hopefully this makes some semblance of sense. But for me, what really helps is the other part of this chart, this right here. I know at first when you look at this, this may look a little scary. But let's actually take a few minutes to go through this. And if we take a few minutes to go through this, I think it can really help us to show what's going on in the heart. Now, just for clarification, as it says here at the top, these are the measures of the pressures associated with the left side of the heart. So notice, for instance, this purple line is the pressure in the left atrium. This blue line is the pressure in the left ventricle. And notice also up here, the green line is the pressure in the ascending aorta. We can ignore that for the most part for right now, but we'll get to there eventually where it's important. So at the very beginning of our cardiac cycle, notice, how do I want to do this? Let's see if white turns out well. The pressure in the atria is slightly greater than the pressure in the ventricle. So during this phase, of course, the atrioventricular valve is open. And during this phase, we are getting our passive filling. of the ventricle. But then notice there's this bump. Why do you think we get this little bump in the pressures of these two?
Is that the start of the contraction
Contraction of what?
of the atria?
Yeah, in fact, notice they've told us this is the atrial systole. Exactly, this little bump is when we are getting that active filling of the ventricle. Because the atria are contracting, increasing their pressure, forcing a little bit more blood into the ventricle. But notice the pressure in the ventricle is still less than the pressure in the atrium. Until this point, hold on, I'm gonna have to use black for this. This point right here. Notice at this point right here, this is when our ventricle starts to contract. So this is when the ventricle starts to contract. And notice the pressure doesn't instantaneously reach its peak. It takes some time to start to increase. So first it starts to go up, and then we get our first major event. What's the big major event that is occurring at this period of time right here? Notice right here, what's happening to the pressure in the ventricle in relation to the pressure of the atrium?
It gets way higher.
Same.
And what's going to happen when the pressure in the ventricle becomes greater than the pressure in the atrium? Exactly. The AV valve closes. And this is when we get our lub. Notice now, but what about our semilunar valves? Are semilunar valves able to overcome the pressure that is inside the aorta?
No.
No. So notice during this period of time that they've kind of drawn here in orange, from basically here to here, notice we are getting an increase in pressure, but all the valves are closed. So are we getting a change in volume?
No.
No.
So what would we call this period of time? And let's go ahead and emphasize it by highlighting in green. What would this period of time right here, where we're getting an increase in pressure, but all the valves are closed, what would we call that period of time?
Isovolumetric contraction.
Perfect. Then notice something else interesting happens. Notice at this point right here, now the pressure in the ventricle, I'm just going to keep starting P because it's less. And the ventricle is now greater than the pressure in the aorta. So what happens at this point?
Semilunar valves open.
And the semilunar valves open because blood is being forced out. This is our ventricular ejection. So notice the pressure in the ventricle continues to climb. And as it continues to climb, it continues to force blood into the aorta. And we have our ventricular ejection. But then our ventricle starts to relax. does its pressure instantaneously go to 0?
No.
No, but it starts to decrease. And notice as it starts to decrease at this point right here, what happens to the pressure in relation to the pressure in our, hold on. What happens to the pressure in our ventricle in relation to the pressure in the aorta?
Comes less.
Oops. Exactly. The pressure in the vent is now less than the pressure in the aorta. And what happens then?
Semilunar valves close.
And we get our dub. Now, before we continue going on in the heart, I want to point out one other thing that's happening here. Notice what happens in the aorta. In the ascending aorta, when that door slams closed, there is a quick spike in pressure. This is what is called the dicrotic notch. Anyone have any idea what might cause this spike in pressure?
Maybe when the doors or like the valves close, they just kind of push like the remaining stuff on top of them back in.
Perfect, absolutely. Let's say you were at a concert, the concert ends and everybody is streaming out of the exits, and then suddenly someone slammed the door closed. Well, what would happen? The first people would bump into the door, and what would the second people do?
Bump into the first people.
And then the third would bump into the second, who would bump into the first again. And suddenly you would get all of these people bumping into each other. A tremendous amount of turbulence. And after all, remember, pressure is just the measure of the number of times things are bouncing into the walls. And if you slam the door on that blood, what's going to happen to the number of times it bounces into the walls?
It will increase or go up.
It's going to increase. So we get that turbulence there in the aorta because we slammed the door on them. And so you're absolutely correct. To slam the door on them, they all bounce into each other and we get that spike of pressure. Now, notice at this point, we have, oops, hold on, I want that to stay pink. I want my highlighter and I want it to be dark red. Notice during this period of time, our pressure in the ventricle is going down. But what is the state of all four of our valves at this point?
Closed.
And because all valves closed, our volume stays the same. And so, of course, what would we call this period of time?
Isovolumetric relaxation.
Absolutely. And lastly, notice there has been a slow but gradual increase in pressure in the atria. And the pressure from the ventricle continues to drop until eventually we reach this magical point right here. And if, of course, this magical point right here, what has happened here? What's happened at this part in the circle?
Pressure in the ventricle. Sorry. Go.
No, you're good. You're good.
Is it maybe that the pressure in the ventricle becomes lower than the atrium?
And when that occurs, what happens?
AV valves open.
and the whole process starts all over again. So like I said, notice this graph is a little scary when you first look at it. But if you actually take the time to look at it, you can truly see how it really is these changes in pressure that are opening and closing the valves and moving the blood. Pressure really does make the world go round, and it certainly makes the cardiac cycle go round. Now notice, this is everything that's happening in the left heart, left side of the heart, not left heart, but left side of the heart, which is dealing with the thicker muscle and the bigger pressures. But the same thing's happening on the right side as well. The pressures just aren't as dramatic. The pressure in the pulmonary trunk, because it's going to the lungs, isn't as high. So we don't need as much pressure to open that valve and move the blood that way. So the numbers may be a little different, but the process is absolutely the same. And one last thing that this shows pretty nicely, right? One of the things that always happens when I go to the doctor, again, like any typical old man, I spend at least 5 or 6 days a week at the doctor's office. And every time I'm there, the first thing that they do is take my blood pressure because they want to make sure it stays stable. And pretty much every time I'm there, because I have a wife, because I have 2 kids in high school, it's usually a pretty solid 340 over 175, which is right about where I like it. And when they talk about those blood pressures, right, we always talk about those 2 numbers, one number over the other number. What do they call the top number?
Systolic.
Systolic. What do they call the bottom number?
Diastolic.
Why? Why is that what they call these numbers?
Is systolic the greatest pressure?
True. And notice it's the greatest pressure because the systolic, really what it's saying is this is when the ventricle is ejecting blood, right? Or we should say ventricle contracting and ejecting blood. Notice that is the highest pressure. And while this person here might not be quite as normal as me, notice there probably looks like somewhere around, oh, we'll call it 118. And the diastolic is, of course, the pressure when the ventricle is in its relaxed state, that lowest value. And notice that looks about, I don't know, we'll call it 78, right? Again, numbers aren't quite as good as mine, but they're not a bad value to have. 118 over 78. I guess for some people that would be okay. I wouldn't want it, but some people would be okay with that. All right. Questions on that? All right, excellent. We did all of that. Again, we talked about the sounds. Remind me again what causes the lub sound?
AV valve
Closing of the
closes.
AV valves.
Closing of the AV valves. And what causes the dub sound?
Semilunar valve.
Closing of the semilunar valves.
Excellent. Do the AV valves and the semilunar valves close at exactly the same time?
No.
No, they are slightly offset. And the good news is it's easy to remember the order because they close in alphabetical order, right? The bicuspid closes before the tricuspid. And notice, even if you call it the mitral valve, it's still in alphabetical order. And then for the dub, the aortic semilunar closes before the pulmonary. Why do you think that might be the case? Why do you think the bicuspid and the aortic semilunar valves close first?
Are they
I would
small?
imagine
Go ahead.
maybe you wouldn't want them both open at the same time. It would just, the blood would go right through.
Well, true. You definitely don't want the bicuspid and the aortic semilunar open at the same time. But remember, the left side of the heart and the right side of the heart don't communicate directly with each other. So when both, and again, it's close. When both of the AV valves close, just one closes just a little bit before the other one. With the semilunar valves, one closes a little bit before the other one. And why do you think it's the bicuspid and the aortic semilunar that close first? Do they share something in common? Well, I'm asking the question, so what's the obvious answer?
They're both on the left side.
They're both on the left side. And as Samuel pointed out, remember the left side is dealing with the higher pressure blood. The bigger, thicker ventricle producing more force, forcing it into that aorta, which has to carry it throughout the body. So the fact that those are dealing with higher pressure blood means that they're going to close a little bit faster. Now notice there's this great picture from your textbook. And again, one of these opportunities we're missing out on. If we were in the classroom, you would actually be trying to isolate individual valves and be able to hear their independent function as we do that. Although, to be honest, we have student stethoscopes, and with 30 of us in a classroom, it's loud, a lot of background noise. So it's not the easiest thing to do anyway, but it is important to appreciate that it is actually possible by localization to be able to kind of isolate each individual valve and check the health of its function. All right, questions on that? Excellent. So here is most of that chart. There is one more piece we have to put into this puzzle, but I think now is a good point to take our second break. So let's go ahead and take our second break now, and then we will add that one last piece to our puzzle here to see how it all goes together. So let's go ahead. So any questions before we take our last break? All right, so we will restart in 15 minutes, which looks like to be 2:46. And I will start the recording at that time. I will see you guys in 15 minutes. So you've had an opportunity to sit and cogitate. So any questions before we dive into the new material? All right, excellent. So as I mentioned, there's one last piece to this we have to put together, and we've kind of already talked about it, but it is, of course, the amount of blood that is moved by the heart. So notice this last part of this chart shows the volume of blood as it changes inside of the left ventricle. Notice again, it starts with a small gradual increase and then a bump in the increase. So I've kind of screwed that up by drawing over the top of it, but there's a little bit of bump there. What causes this general increase and then that tiny little bump? Well, let's be more precise then. My microphone is on, right? I am speaking out loud. What's occurring during this part of the curve?
Passive blood.
Yeah, passive filling of the ventricle. And what's happening here?
Active.
There you go, active filling. There you go, perfect. Notice there is a brief period of time where there is no change in the volume. What might be happening during that period of time where there is no change?
Isovolumetric contraction.
Excellent. Notice then there is a rapid decrease in the volume of blood in the ventricle. What's happening during that phase?
Ventricular ejection.
Excellent. Then there's a brief period of time where the pressure stays the same. What's happening there?
Isovolumetric relaxation.
There you go. And then that leaves to, once again, the then passive and then the active filling of the ventricle. So we can see, again, all those changes or lack of changes in volume when we hit the 2 isovolumetric periods that are taking place. Notice that also shows us that our end diastolic volume is the highest volume of blood that you'll have in the ventricle. The end systolic volume is the lowest volume of blood that you'll have in the ventricle. So notice when we're talking about the left ventricle here, if we want to know how much blood is moved in 1 cardiac cycle, then as we talked about last time, all we have to do is take the end diastolic volume and subtract the end systolic volume. And luckily they've given us some values here. The end diastolic volume is 120. The end systolic volume is 50. So how much blood is moved from the left ventricle in 1 cardiac cycle?
70
70
milliliters.
milliliters.
There you go. This is what is known as the stroke volume. And notice when we talk about the stroke volume, we're just talking about the left ventricle. What do you think the stroke volume of the right ventricle would be? You don't have to
Lower?
give me an absolute number. Do you think it'd be more or less?
Less.
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 Definitely remember the right side uses less pressures. However, isn't our cardiovascular system a closed system? Yeah, if the left side of our heart was always pumping 50 milliliters out and the right side, 70, and the right side was always pushing out 50 milliliters, after a while, could that cause a problem?
Yeah.
Yeah. So I'll ask the question again. We absolutely know with 100% certainty that the right side uses less pressure, but how much blood does it actually move?
The same.
Same.
Exactly.
70 mil.
So the stroke volume of the right ventricle is the same. All right. Questions on that? So we know 1 ventricle moves 70 milliliters of blood in 1 cardiac cycle. How many cardiac cycles do you have in a minute?
Around 60.
60?
Is it 70?
70? That kind of depends on the person, right? What would be another name for the number of cardiac cycles you had in a minute?
Cardiac output.
No, not quite. We're getting there. We're getting there. What is
Is
the
it
term
your
you
heart
use
rate?
to describe? Yeah, exactly. Your heart rate is the total number of cardiac cycles you have in what?
1 minute.
1 minute. Excellent. So what's a good number for that?
90 to 100.
I think 60 is a little low. I think 90 is a little high. Let's split the difference. Let's say a nice resting heart rate of, I don't know, let's say 80. or 75 or something like that. We'll go 80 because it makes the math simple. All right. Excellent. Now, if I wanted to know how much blood was moved by the heart, pardon me, by one ventricle in 1 minute of time, what would I do?
Multiply 70 milliliters by 80 pumps per minute.
Let's say cycles. Excellent. And what would that equal?
5,600 milliliters of blood per minute.
Per minute. And what is your blood volume on average? I know we haven't necessarily talked about it in this class, so we may have mentioned it at the very beginning.
5 liters.
Yeah, somewhere between 5 and 6 liters for the average person. So notice in 1 minute of time, your heart moves your entire volume of blood through it. And of course, we give a fancy name for this, and I think someone mentioned it earlier. This amount of blood moved by one ventricle in 1 minute of time, we call the cardiac output.
So the cardiac output measurement is for 1 minute of time.
Yes, is the amount of from one ventricle in 1 minute of time.
Thank you.
Now, again, the one more point I want to emphasize. When do we reach our end diastolic volume? What's the event that occurs or events that occur that cause us to reach our end diastolic volume?
Atrial systole.
Excellent. So our ventricle begins to contract. And what is it about that beginning of the contraction that causes us to reach the end diastolic volume?
Increases pressure.
And what does that pressure do?
Forces the last 20% of blood out.
No, this isn't. No, the contraction of the ventricle isn't what forces the blood into it. What's the event that occurs when the ventricle starts to contract that causes us to reach our end diastolic volume? There we go. Amanda's got it. Our AV valve closes. All right, it's that closing of the AV valve. No more blood can get into the ventricle, and we've reached the amount. And by the same token, what causes the end systolic volume? Yes, I'm very happy that I took the moment to ask these questions. There we go. What causes the semilunar valve to close?
Pressure from the ascending aorta.
Yeah, the ventricle begins to relax. And remember, as the ventricle begins to relax, its pressure starts to drop, becomes less than in the aorta. And when that pressure when the ventricle starts to relax, the semilunar valve closes. And when that semilunar valve closes, then we've reached the end systolic volume. Excellent. So again, we've defined our heart rate. The cardiac cycle at rest is about 0.8 seconds. So that works at about 75 beats per minute. As we mentioned, our stroke volume is how much blood is pumped out of one ventricle in one heartbeat. And again, we figured that out by taking the end diastolic volume and subtracting the end systolic volume, which we learned was 120 minus 50, and that equaled 70 milliliters. And so, like I said, when we put those two together, we get our cardiac output. So as I mentioned, cardiac output, we use 75 beats per minute. That works out to about 5250. If we go with 80 beats a minute, then as we said, it was 56. But since the average blood is between 5 and 6 liters, as I mentioned, every minute, your entire blood volume moves through one side of your heart, really both sides of the heart. Now, the other key is this is happening at rest. Do we need to be able to modify and change our cardiac output depending on our activity levels?
Yeah.
Yeah, absolutely. Right. When we are active, we need more. Now, as I mentioned, let's go with very simple numbers here. We'll round this down to 5 liters at rest. Obviously, your heart can do more when you are active. And so for mere mortals like you and I, if we're measuring our cardiac reserve is a measure of what our maximal cardiac output is over our cardiac output at rest. And for mere mortals like you and me, that usually equals at about 4 or 5. So the ratio is about 5 to 1. We'll go with 5 to 1 because it's a nice, easy number. So what would your maximal cardiac output go? If your cardiac reserve was a 5, how much blood would your heart be able to pump at its maximal level of activity?
25 milliliters.
25, not milliliters, 25 liters. In a single minute of time, your heart could pump 25 liters of blood through that ventricle in a single minute. Now, obviously, can it sustain that for a prolonged period of time? No, but it is incredibly impressive. However, what's even more impressive are professional athletes. Some professional athletes can have a cardiac reserve around 8, meaning that in a single minute of time, they can pump 35 liters of blood through their left ventricle and therefore through their right ventricle in a single minute of time. All right, this is how people like Usain Bolt get the energy and the resources and the fuels necessary to be able to run that 100 meters in less than 10 seconds. Because we have this.
Is that,
go ahead.
is that genetic, or can you like build yourself up to that?
Yes. Right. Again, we'll think of it in simpler terms. If it doesn't even have to be running, well, let's go with running. Running would be easier. If we were to all line up outside right now and do a 100-yard dash, right, we'd all have whatever our times are. If we all continue to do that 15 times a day, every day for the rest of the semester. If so, for the rest of the semester, every single day, we're all going outside and we're running 1,500-yard dashes. At the end of the semester, would we all be faster? Yeah,
Yes,
absolutely.
most likely.
But would we all have had an equal increase in our speed?
No.
No. So yes, training can improve these things, but genetics also gives you your starting point and also your potential to be able to improve, right? Genetically, some people have more fast oxidative muscles in their legs and some people have less. And so yes, absolutely, genetics plays a role in it. But at the same point, if Usain Bolt decided tomorrow he wanted to be a world-class marathonist, would he be able to instantly become a world-class marathonist?
No.
No, because he's been training that fast twitch muscles in his leg, and he uses very different muscle type, very different use of those muscles for running a marathon. So again, could he train? Could he potentially get there eventually? Maybe, but it wouldn't be instantaneous. So yes, some of it is genetic, some of it is training. All right. Excellent. Questions on this?
Yeah, so Would all the values technically be doubled because it's only one ventricle? I'm kind of confused.
Well, so what you got to remember is the heart is basically two related pumps. One dealing with the oxygen poor blood and one dealing with the oxygen rich blood. So when we talk about the cardiac output, that is a measure of what's happening in one ventricle. And whatever's happening in one ventricle is happening in the other. So you are correct. When we talk about moving 5 liters of blood out of the left side of your heart, you are correct. The right side is also moving 5 liters of blood at the same time. But you wouldn't say the cardiac output is 10, because the cardiac output is a measure of what's just happening in one ventricle. So by definition, cardiac output is just one ventricle, because stroke volume is just one ventricle. Since stroke volume is just one ventricle, cardiac output is just one ventricle. But you've hit on a very excellent point. As we just finished pointing out, there are times when we want to modify our cardiac output. And what are the 2 main factors we would need to control to be able to modify our cardiac output? Not a trick question. If I wanted to
Stroke volume,
change
heart rate.
Heart rate,
I'd have to change heart rate. And what'd be the other thing I could change?
stroke volume.
Stroke volume. There you go. So by modifying my heart rate, modifying my stroke volume, I can change my cardiac output. And is it important for us to know how to do that?
Yes.
Yeah, absolutely. Now, luckily, some of this we've already talked about. We know the heart has an intrinsic rate, but what are the 2 factors we can use to modify heart rate?
Sympathetic, parasympathetic system.
Yeah, so our autonomic nervous system can influence heart rate. Is there anything else that can influence heart rate?
Hormones.
There we go. See how easy that was? Excellent. And since we know how to calculate stroke volume, and stroke volume is the relationship between the amount of blood we can essentially get into the ventricle and the end systolic volume, which is basically the amount of blood I can get out of the ventricle. So if I can change those 2 things, I can change stroke volume. And if I can change stroke volume, I can change cardiac output. Let's start easy. The ones we've already talked about. Autonomic nervous system. Remind me again how our sympathetic nervous system can affect heart rate. It increases it. Excellent. By doing what?
Opening sodium channels.
With what? What is it used to open those sodium channels?
Norepinephrine.
Norepinephrine.
Excellent. And epinephrine, right, from the from our adrenal gland. And how does the parasympathetic do it again?
Decreases.
How?
Chlorine channels with acetylcholine.
And let's take this one step further. If my sympathetic nervous system uses uses norepinephrine and epinephrine to open sodium channels and increases heart rate, what effect does that have on my cardiac output?
Increases.
There you go. And so then conversely, parasympathetic, that's not even. Parasympathetic is going to have what effect on the cardiac output?
Decrease.
There you go. Again, no new information here. We've done this 3 times. However, we've described this like 3 times now. So is that something that you want to make sure you're comfortable with and understand for the exam?
Yep.
Yes.
I would think that that's probably definitely the case. Absolutely. Perfect. And of course, we have these baroreceptors that measure the pressure that help us to maintain appropriate blood pressure and maintain appropriate cardiovascular flow. Excellent. So our cardiac output. So again, we've described this. There's no new information here. We've done this already. And I think we've kind of talked already about chemicals as well. We've talked about how hormones like epinephrine, norepinephrine, also T3 and T4. Anybody, we haven't talked about the endocrine system yet, but anybody know what gland releases T3 and T4?
The thyroid.
Thyroid gland plays, I agree. The thyroid gland plays a major role in overall metabolism of the body. So if we increase the amount of these thyroid hormones, then typically heart rate is going to go up, cardiac output is going to go up. And if we decrease the amount, heart rate goes down, cardiac output goes down. Ion levels, changes in sodium, potassium, and calcium levels can modify heart rate. But there are other factors that can as well. Age. What typically happens to our heart rate as we age?
Slower.
Slows down.
Increases.
Well, I guess it really depends on what we're talking about. How about an infant's heart rate? What's an infant's heart rate like?
It's really fast.
115, 120.
Super fast, absolutely. It's almost alien when you listen to that because it has such a small volume and it has so much work to do and the metabolism of the baby is so high. So definitely as you go from infant towards adolescent and adulthood, then certainly heart rate goes down. But what happens as you continue from adulthood on to becoming more elderly?
Does it go back up a little bit?
It does start to go up. Why might it start to go back up?
The muscles have to
Muscle
work
fatigue.
harder.
Yeah, well, part of it could be muscle fatigue. Some of it could be a loss of elasticity of the blood vessels. So blood doesn't flow as easily through it. So the heart has to work a little bit harder, right? And things like that. All those are things that could cause less efficiency. And so then the heart rate has to go up to maintain it. How does gender affect heart rate? Who typically has a higher heart rate, males or females?
Males.
Males.
Males actually tend to have a lower heart rate than females. Anyone know
I know
why?
I don't know why, but I know sometimes with babies, they use heart rate, like a higher heart rate to determine if it's a girl. I know it's a myth, but I've just
Yeah,
heard.
that's like saying size. Again, it's one of those things that there may be some statistical mathematical significance to it, but it's not meaningful. Heart size is a perfect example. Statistically, males are taller than females. But even in a class of 30 students like we have right here, is every single male taller than every single female in a class like this?
No.
No.
So those kind of changes, those kind of variations, while, like I said, while the math may show some statistical significance, there's no meaningful significance to that. And it's the same way with that. There's so much variation, it isn't necessarily meaningful. And exactly, Maximilian's got it. Males typically have larger bodies, and the larger the body, typically the lower the heart rate, right? The hummingbird has a much faster heart rate than the elephant. And so again, it's not meaningful, but mathematically, statistically, it is a little bit significant. What about physical fitness? How does that affect heart rate?
Muscle mass.
Lower, absolutely. The heart, again, is a muscle. And the more it's used, the more efficient it becomes. So typically with athletes or as we're more physically fit, our heart rate typically tends to decrease because of that increase in fitness, the increase in efficiency. And how does temperature affect heart rate?
Increase.
When temperature goes up, what happens to heart rate?
Increases.
It increases as well, absolutely. This is one of those problems with the polar plunges, right? The Winter equinox is right around the corner. And one of the things they do in Chicago is on the winter equinox, everybody goes and jumps into the river, right? It's a big, huge celebration that they all do. And one of the problems with that is when you have that rapid decrease in temperature from jumping into freezing cold water, it can actually cause a physiological change where the heart rate decreases dramatically. And if the shock is too sudden, the drop in temperature is too sudden, the heart can actually stop beating as a result of that rapid temperature change. So don't jump into frozen lakes.
So does it increase because it's pumping more blood to the surface of the skin and there's vasodilation going on for sweat evaporation?
It seems like a reasonable explanation. I was trying to flip it around to see if then would it make sense that with a colder temperature, you would want to slow the heart down to bring less blood to the surface. Sure, I'll buy that. Again, one of the things you got to remember is why is always one of those questions that is very difficult to answer in anatomy and physiology. We can often infer or guess at why things are the way they are. And some of them are pretty common sense, and some of them we have absolutely no clue of. In fact, we'll see that when we look at some of the blood vessels later on. But we have to remember that ultimately, the engineer that designed all this didn't leave us her footnotes. And so as a result of that, we don't necessarily know why things are. However, from a physics standpoint, what you say certainly makes sense. So my guess is that seems like as reasonable, if not better, of a reasonable explanation than anything else that I've heard. Yeah. All right. So again, that's our changing of our heart rate, and really isn't any new information. This is stuff we kind of already learned about and understood and should make sense. So what we need to talk a little bit more to make sure we understand is how we affect stroke volume. As we mentioned, to influence stroke volume, there's one of two things we want to change. We either want to change the end diastolic volume, or we want to change the end systolic volume. And again, remember the end diastolic volume is how much blood we get in. And the end systolic is how much blood we get out. So let's talk about changing the end diastolic volume first. Let's say, for instance, you had a water balloon that you wanted to fill with water. How could you get more water into that water balloon?
Stretching it?
Okay, stretching it could be something that helps. We could change, make it easier. Really, you're breaking the surface tension to make it easier to get water inside. So yeah, we'll definitely talk about stretch. What else?
Increase preload.
What does that mean though? Increase in preload means we want to get more blood in there. We want to get more water. So I have a sink and I have a water balloon. And up till now, I've been filling the water balloons by putting them on the faucet, holding it there on the spout for 5 seconds, and then taking it away. And I get a set amount of water into that balloon. How could I get more into that balloon?
Hold it there longer.
Yeah, one way is to hold it there longer.
Or change the pressure of the water.
Or I could turn up the water. Absolutely. And again, as was mentioned, that is the preload. Preload is how much blood we can get in. And there are two main ways we can do that. One is we can delay the contraction of the ventricle. If we can delay contraction of the ventricle, then our AV valve stays open longer. And if it stays open longer, we can get more blood in it. But as you also mentioned, we can also turn up the valve. We can constrict peripheral veins. And when we do that, we force the blood back to the heart more quickly. It's like increasing the stream. Blood comes back to the heart more quickly and it fills it more rapidly. So notice whether we turn up the faucet or whether we hold it there longer, we can get more blood into the ventricle. But let's get back to that idea of, actually, I want that up at the top. Let's get back to that point you were talking about with stretch, because here's the problem. If we add a bunch of water to a water balloon, doesn't the water balloon become more unwieldy, harder to hold, harder to throw, less efficient? If we fill up the heart too much, if we fill the heart with all this blood, it may not be as efficient. But it turns out there's a characteristic of the heart that helps it in this fashion. It is what is known as the Frank-Starling law of the heart. This was, not surprisingly, described by two physiologists, good old Bob Frank and Bob Starling, one from the US, one from England, at very close to the same period of time. They both described this. They both wrote up papers, they both presented them to their medical groups, and a huge debate occurred because of this as to who should get credit. And as you can see, the short version of the story, how it got resolved, is they both got their names on it, but it was a shockingly tense and vigorously debated event that if you're ever having trouble sleeping at night, I encourage you to look it up and read the story of the Frank-Starling law of the heart. But what it tells us is that as the heart stretches, as more blood fills into the heart is actually able to increase the force of its contractions. Now, how might this occur? Think back to 430. One of the things that we learned about in 430 are ways that we could modify the tension produced, or the force produced in a muscle contraction. And what were the two factors that we talked about that could cause an increase in the tension of a muscle contraction? Does anybody remember? I'll give you a hint. One is to increase the stimulation. And I give you that hint because that's not the one we care about. What was the other thing we could change about a muscle cell to change how much tension it produced?
How much overlap?
Excellent. The length of the muscle. Remember, as we talked about, as we stretch the muscle out or shorten the muscle, we had either more or less overlap between the actin and the myosin. Remember, as we talked about, if you stretched a muscle way far out, like that bouncer holding your arm behind you when you're getting all drunk and disorderly at the bar, by stretching the muscle out, there's less overlap between the actin and the myosin. And as a result of that, less tension is produced. However, if they're too close together, there's plenty of overlap. The myosin can grab onto the actin, but there's no place to perform the power strokes. There's no place for the myosin heads to go. And so we have less tension. Well, what happens is that the heart in its resting state isn't at its optimal length. So as it fills with more blood, it actually gets to a more optimal length and becomes more efficient. So as the heart actually increases in its stretch, the force of the contraction it is going to produce becomes greater. And your book's got a pretty picture to emphasize this point. The more stretch we get, the more preload we get, the more blood we get into the ventricles, the more the ventricles are going to stretch, and the stronger the contraction it will produce. So yes, we're putting more blood into it, but we're also able to move more blood as well. All right. Questions on that? Now, go ahead.
I was just answering no.
Oh, okay. Notice along the same lines, as I mentioned, the ability to stimulate the muscle cells has that ability to increase the contractility. Remember, we talked about how the sympathetic actually innervates the ventricles, the Purkinje fibers, to be able to stimulate them to contract more. So that sympathetic neurotransmitters, adrenaline, right? When someone jumps out and scares you, your heart, you can feel it pounding in your chest. And even calcium and potassium levels, all of those are things that can affect how strong the contraction is, the intensity of that contraction. And obviously, the stronger the contraction, the more the blood moves. So stronger contraction is going to increase our stroke volume. And increase in our stroke volume means a greater cardiac output. However, and actually, I'm going to cheat. Actually, no, I'm not. We'll just do it this way. Here's my ventricle. Nope, that's not what I wanted. Here's my aorta. And of course, in between them, I have those semilunar valves. Now, what do I need to do to get those semilunar valves to open to eject the blood?
Pressure inside the ventricle higher than the ascending aorta.
Excellent. So basically, we need to get the pressure in here to be greater than the pressure out here. With that contractility, as we mentioned, we have the ability to increase that pressure. But can anything affect the pressure in the arteries?
Yeah.
Yeah. In fact, what do we call the pressure in our arteries? Not a trick question.
Blood pressure.
Yeah, we
Blood
call it the
pressure.
blood pressure. If, like me, your blood pressure is 427 over 218,
Need to call an ambulance.
no, it's like I said, it's right in the wheelhouse, right where I like it. But think about it this way. If you have chronic high blood pressure, for your heart to be able to put the same volume of blood out into your arteries, it's going to have to produce a much greater pressure. And to produce a much greater pressure, it's going to have to work harder. But that's okay. It only has to work harder on that one cardiac cycle. But how many cardiac cycles do you have in a minute?
75.
70?
75. And how many minutes in an hour?
60.
So how many cardiac cycles is that in an hour? And how many hours in a day? And how many days in a week? Right?
A
I'm
lot.
not sure the exact number, but I'm sure a lot is definitely one of them. Absolutely. And if you think about it, in all of those, a lot of heart rate beats, if the heart has to work that much harder to overcome the afterload. And that's really, when we talk about the afterload, that's what we're talking about. We're talking about the pressure in the artery that the ventricle must overcome. If you have chronic high blood pressure, your heart is constantly having to work harder and harder to get that blood pumped out. And it can cause muscle fatigue of the heart and can lead to all sorts of different types of problems with the heart from that chronic high blood pressure. So that force that must be overcome, we call that afterload. That force of the blood in the aorta, really. Again, it's not as big of a issue in the pulmonary trunk. Primarily, we're talking about that systemic blood pressure, that aorta. And again, if you remember, we talked about it's that atrial semilunar valve, which is the one that is most likely to be damaged, to prolapse, because it's the one dealing with the greatest pressures. All right. So there you go. Here we see all those factors working together, influencing the to cause our cardiac output from this young woman who, as you can see, is clearly running from a bear with an axe. All right. Questions on that? Excellent. So affect stroke volume, affect heart rate, affect cardiac output. All right, one last important, how are we on time? We're doing awesome on time. Again, we've now described the basic cardiac function, but as we've talked about, sometimes we are not able to maintain homeostasis, and we have those homeostatic imbalances, and that occurs when the heart cannot pump enough blood to meet the demands of the body. If this is caused by a problem of the heart, there can be other causes that we'll talk about with blood vessels and stuff like that. But if it's caused by a problem of the heart, we typically refer to this as congestive heart failure. Now, this congestive heart failure, when it first presents, typically presents asymmetrically. And depending on which side of the heart is having difficulty moving the blood, you can have pulmonary congestion or you can have peripheral congestion. I think we talked about this briefly before, but I want to make a point of emphasizing this again, because I don't think it's always necessarily intuitive. So here is my heart. Here are the two sides. Here are that, and again, veins in, arteries out. I'm not going to bother erasing the lines or doing any of that kind of stuff. Actually, I am. Apparently, I'm more anal than I thought. All right, so at least do a half-assed job of it. Oops. Perfect. But I'm not drawing the valves. All right, excellent. So what do you think the symptoms of pulmonary congestion are?
Pressure in the chest.
Okay, excellent. You get an increased pressure in the chest.
Difficulty breathing.
Difficulty breathing, especially when laying down. All right, absolutely, exactly. All right, you have that. And problems with which sides of the heart would cause this pulmonary congestion?
Would it be the right
Right
side?
side.
Excellent. I kind of heard a mix of answers there. So this is a perfect opportunity for a poll. Excellent. So A, if you think it is the left side, B, if you think it is the right side of the heart. So pulmonary congestion caused by right side or left side problems. Excellent. I don't remember what I said. Is A left or is A right?
Left.
Okay, A is left, perfect. And B is right. Excellent. All right, not everybody's, we're getting closer and closer. It's actually a lot closer than I thought. 13 are saying B, 9 are saying A. So let's figure this out. That's a good stopping point. That's good enough. It's a good mix, just as I kind of expected. So the majority said B, so that is the right side. So let's say that the right side is the one that has the problem. Now, again, as I've mentioned before, I think it is easiest to think of this in terms of completely unrealistic, simple numbers. So let's say that the left ventricle normally pumps out 10 milliliters of blood. So it pumps out 10 milliliters of blood. And if it's pumping out 10 milliliters of blood, how much blood is normally being pumped out by the right side?
10 milliliters.
10 milliliters. Excellent, because we know that they should be the same. So now here's the next question. How much blood should be coming back to the right side?
10 milliliters.
10 milliliters. And how much blood should be coming back to the left side?
10 milliliters.
Exactly, 17 milliliters. No, I'm just kidding. 10 milliliters. Excellent. Perfect. Continuous cycle. Bing, bang, bong. Everything is awesome. Except, as we've mentioned now, there is a problem with the right side of the heart. And now suddenly the right side of the heart is no longer pumping out because it's losing its efficiency. It's no longer pumping out 10 milliliters of blood. It is now only pumping out 7. So the left side pumps out 10, the right side pumps out 7, and 10 comes back. And of that 10, how much gets pumped out?
7.
Right, and 10 more come back. And how much gets pumped out?
7.
7. Notice what's going to start to happen is we are going to start to have congestion in the right side of the heart because the blood is backing up. And as the blood backs up in the right side of the heart, where does that backed up blood go?
The right ventricle.
Well, it's started in the right ventricle. From there,
Right
from the right
atria.
ventricle, it's going to go into the right atria. And from the right atria, where does it back up?
From the vena cava.
Right. It backs up into the systemic blood vessels. Would that cause that pulmonary congestion we just finished talking about?
No.
No. Notice that's not going to cause that. What problems with the right side of the heart are actually going to do is they are going to cause systemic congestion. And what are those symptoms of the systemic congestion going to be?
Edema.
Yeah. Edema, especially in the lower appendages, swelling of the joints, right? Loss of mobility. Again, this is one of the reasons why I wanted to take the time to do this. Yes, the right side is the part that is responsible for pumping blood to the lungs. But when there's problems with the right side, what actually happens is it backs up and congests into the systemic circulation. And therefore, pulmonary congestion is actually caused by problems. Oops, that's not how you spell problems. With the left side. Now, we mentioned that it starts asymmetrically, but is it going to stay asymmetrical?
No.
No, typically it will spread from one side to another. So again, I think the symptoms of pulmonary and peripheral congestion are obvious to us, but the causes aren't always. So I wanted to make a point of emphasizing that difference and distinction there. All right, questions on that?
In the symptoms of pulmonary congestion,
Yes.
is it just unilateral edema, like the right leg versus the left, or is it both? Or could it be both, or either or?
Typically, great question. Typically, it is going to be both. But is it going to necessarily be symmetrical? No. And in fact, because of the difference in piping, you do tend to get a little bit more in the left side because that's where the heart is. It's close, so it tends to have more of an impact, more congestion into the left side first. But again, it's going to affect both sides typically. Yeah. Great question. Any others? All right, excellent. Hopefully that is everything you wanted to know and more about the heart. So now that we understand that, we can switch gears now and talk a little bit about the blood vessels. Now, we don't have a tremendous amount of time, but I do want to take advantage of some of it. So let's go ahead and take one more 15-minute break. Let's come back, and here I'm going to go do it here so that's easy for me to come back to. We will restart in 15 minutes, which will be 3:56. And we're not going to cover a ton of information, but I do want to get ahead because the more we're ahead, the more time we'll actually have to do the systemic anatomy of the blood vessels, which I want to have time to do. So at 3:56, we will restart. And at that point, we will focus on the basic blood vessel anatomy. So we will do that when we come back from the break. All right. Questions on that? All right. I will see you guys in 15 minutes. All righty. Before we dive into the blood vessel stuff, I did want to, because we covered a lot of physiology today, and I know that can be challenging. And so this is a perfect opportunity. I gave you that interactive physiology exercise to encourage you to take advantage of that. But if you haven't looked at it yet, when you come to your study area in the Mastering A&P, and you go to the interactive physiology, notice there's a massive amount of stuff on the cardiovascular system. And in fact, if we look at cardiac cycle, the second activity right here, this is a great resource. It talks about our goals for this. Then there are, again, some concepts of the anatomy and things that if you're unclear about, it can get you started. And then, like I said, this is a great interactive tutorial. It starts with a video, an animation that walks you through the process.
The cardiac cycle is the sequence of events that propels blood through the heart.
Can you guys hear that?
Yeah.
Okay.
Yeah.
During one complete heartbeat. Your heart beats in a continuous cycle, represented here as a clock. The cycle alternates between periods of contraction or systole and relaxation or diastole.
And so again, you can watch the video that goes through this, and then there are all a bunch of activities. This one happens to have a rodeo activity where you get to be a red blood cell and decide which side of the heart you want to go through. And so we're going to go through the left side and we're going to herd.
Professor?
Yes.
I don't know how it is for everyone else, but I can't see your screen.
Same.
Oh,
Same with me.
my apologies. Let's try this again. All right, so from your study area in the Master in A&P, you'd go to the interactive physiology. In the can you guys see it now?
Yes.
Okay. Interactive physiology. Notice the second activity is the cardiac cycle. And so let's go ahead and go back all the way to the beginning. So for the cardiac cycle, gives us our learning goals. On the second page, it gives us some links to information if there's some concepts we're not clear about. If we need to go back and look at the waveforms of the ECG, we can do that, or things along those lines. And then, like I said, they have these great videos. So here's that video that you guys apparently heard and didn't see.
The cardiac cycle is the sequence of events that propels blood through the heart during one complete heartbeat.
And then, as I mentioned, it's an interactive tutorial. So after you watch the video, as I mentioned, there's a red blood cell roundup you get to do, where if we decide we want to do the left side of the heart, we're going to herd our blood through the left side. Okay, some of them a little dorky, but you get the idea. It's going to walk you through. It's going to have you identify, all right, we want to get blood from our, since we're on the left side, from the pulmonary veins into the heart. So we can click on that and then submit it and see if we got it correct, and so on and so forth. So there are some tremendous tools that if you're struggling with this material, make sure you're using and taking advantage of. So by all means, again, I as a carrot, giving you that assignment on the interactive physiology to encourage you to go to look at it, but make sure you're taking advantage of the resources that are here, especially if you paid for them. These are things you paid for. So if you're struggling with these concepts, definitely contact me, definitely work in your study groups, but also take advantage of the resources that you paid good money to get. So make sure you're taking advantage of all of those, because like I said, they have visual, they have tactile, all sorts of different activities to help you to be successful. So it's a really, really great tool. So if you're not using them, I want to strongly encourage you to. All right, with the little bit of time we have left, I wanted to just start our introduction to the anatomy of our blood vessels. Here we see the rest of the cardiovascular system. We've spent all our time talking about the heart, but we have all these blood vessels we need to discuss as well. And as we mentioned at first, there are 3, but really there are 5 main types of blood vessels. What were the big 3 that we had already identified?
Arteries, veins, capillaries.
Excellent. So we have our arteries. And how did we define that artery?
Oxygen rich.
That is not how we defined it, because while most arteries are oxygen rich, all is not, most is not all. So if we're going to talk about arteries, what is the characteristic that 100% of all arteries share?
Flow away from the heart.
Exactly, the direction they carry the blood, and they carry blood away from the heart. Excellent. And so then, of course, veins do what?
Carry blood to the heart.
And then, as you pointed out, in between them, we have our capillaries. They're the turnaround point in the body where things turn around and go back. I think I saw somewhere that every single living cell in the body is something like 0.3 microns away from a capillary, or some crazy number like that. So yes, they're definitely the turnaround point, but what's obviously the big function of the capillaries?
Gas exchange.
Well, not just gas exchange, but all exchange of materials. All exchange of materials that occur with the blood, right? Whether it's blood and the air in the lungs, whether it is blood in the tissues of the body, all exchange of materials take place from a capillary. Excellent. Oops, I spelled that wrong. From a capillary. Excellent. However, as I also mentioned, there are two other major types of blood vessels. There you go. Garvett's got it. The first are arterioles. Now, obviously, as the name might indicate, arterioles are mostly small arteries. But there's two other keys to their definition. Anatomically, they are distinct from the arteries. And we have to talk about the anatomy to see what that is. But also, these are the ones that feed directly into capillaries. And so not surprisingly, a venule receives blood. Well, let's say it this way, is a small vein. Oops, why is that not writing? So it receives blood directly from the capillary and is a small vein. However, unlike arterioles, a venule really is only distinguished from a vein by its size. There isn't the same anatomical differences the way there are between an artery and an arteriole. So there you go. Those are indeed our 5 main types of blood vessels: arteries, arterioles, capillaries, venules, and veins. I guess I need to make that plural so that for consistency. Excellent. So we can erase that. We did all of that. And again, if you were to take every single blood vessel out of your body and lay it out in a row, it would hurt a lot. All right, questions on that? All right. Obviously, there are some anatomical differences between these 3 things, but there are also some tremendous similarities as well. So when we look at the anatomy of a blood vessel, most blood vessels, and this is probably a good time for our whiteboard. Most blood vessels have 3 distinct layers, or what are called tunics. Let's start from the lumen. So let's say, for instance, rather than drawing it all the way around, I'll just draw it this way. So here is our lumen of our blood vessel. So the surface that is closest to the lumen is what is known as the tunica intima. Or the tunica interna. And essentially, this is the layer that is continuous with the endocardium. Remember, we talked about the inside lining of the heart had a nice smooth surface to reduce the turbulence that was being produced. And so, not surprisingly, that was lined by an epithelial tissue, and on top of that was a connective tissue. And does anybody remember what epithelial tissue forms the endocardium?
Simple squamous.
Simple squamous, excellent. Excellent. And what was the connective tissue?
Areolar.
Excellent. So there you go. We are going to have here lining our surface, a simple squamous epithelial tissue. And an areolar connective tissue, which I'll draw this way. All right, with me so far?
Yeah.
Yes.
All right, excellent. Now, this is true for both arteries and veins. However, in arteries only, there is a thin layer of elastic fibers within this tunica intima. And this thin layer of elastic fibers allows it to deal with the constant changes in pressure inside of the arteries. And this is known as the internal elastic membrane. So this internal elastic membrane allows our arteries to deal with the higher pressure and the more dramatic changes of pressure in the artery. Remember, arteries are basically receiving blood from the heart and carrying it away from the heart. And as we know, the heart's not a faucet that you turn on and water flows continuously. As we know, there's a period of time with that ventricular contraction, that ventricular ejection, that a large bolus of blood is pushed into an artery. And so an artery needs to be able to expand to accommodate that big bolus of blood. Of course, as soon as the pressure drops in the ventricle and it stops pushing blood into the artery, do we want the pressure to plummet as a result of no more blood being pushed into it? Well, what makes the world go round? Pressure makes the world go round. Exactly. So then we need that elastic membrane to then be able to recoil like a rubber band to maintain that higher pressure. So that ability to stretch and recoil helps to maintain a more consistent pressure in our artery. And so in our artery, we have in the middle of our tunica intima, this internal elastic membrane. All right, questions on that? Excellent. Guess what the middle layer of a blood vessel is?
Blood.
Well, remember, blood's in the lumen. So we're talking about the wall. So what do you think the middle layer of the wall of our
Smooth muscle?
Tunica media.
It is indeed the tunica media, and it is indeed made up of smooth muscle. Absolutely. So we have our tunica media layer here, and it is indeed comprised of smooth muscle. And more specifically, circular smooth muscle wrapping around the lumen. So again, if we were to cheat a little bit here, that's not going to work. Do it this way. So again, it wraps around the lumen of the blood vessel. Why would we want that circular muscle layer there? What would a circular layer of muscle do?
Constrict it?
Yeah. So when it dilates and constricts the blood vessel, it changes the diameter. And if we decrease the diameter, increase the resistance and less blood flows. Whereas if we relax the blood vessel, then more blood flows in that area and we get an increase in blood flow. So it allows us to change the diameter and allows us to change our blood flow. Quick question. What branch of the nervous system controls the tunica media?
Autonomic.
Sympathetic.
Right. So is it both branches of the autonomic? I think
Yeah.
Jacob already said it, but yeah. Now remember, this is sympathetic only. Remember, for most blood vessels, it is just the sympathetic nervous system that changes the diameter of the blood vessels. The same way that the sympathetic's the one that innervates the ventricles, it's also the only one that innervates the blood vessels. So as we mentioned, our sympathetic has a much greater effect on blood pressure than our parasympathetic does. Lastly, we have the outermost layer, the tunica externa. And this tunica externa is basically just a fibrous connective tissue layer. Why? Why might we want a big fibrous connective tissue layer around the outside of our blood vessel?
Protection, insulation.
Absolutely, it provides protection. It does something else as well. What else does it do?
Structure.
What do you mean by structure? I like that, but be more specific.
It
I'm sorry, go ahead. Someone was trying to help Jacob. What else? What do we mean by structure? What else does this tunica externa do? Well, I'll ask the question this way. How many people here have either given blood or taken blood? No one here has given blood before?
I have.
Okay, excellent. I was going to say, I was worried that a bunch of you people were very, very horrible people. Excellent. All right. Hopefully you've either taken blood or given blood. Absolutely. And when the nurse comes to take the blood out of your arm, does she have to chase your blood vessel all over the place? Are your blood vessels moving around like wiggly worms underneath your skin?
No.
No. Why
No.
not? Well, because they're anchored in place. Basically, this fibrous tunica externa connects it to the surrounding tissue. Again, this is true for all of our blood vessels, or most of our blood vessels, I should say. But again, there is another distinction, really two, in arteries. In arteries, there is also an external elastic membrane. Right? If we're going to have an internal something, we're going to have an external something. And being the external elastic membrane, it must be part of the tunica externa, right?
Wrong.
Yeah, anatomists hate us. But if we have an internal something, we have an external something. So you are absolutely correct. The external elastic membrane is part of the tunica media. And also in arteries or veins, which do you think has a thicker tunica media? Arteries or veins?
Arteries.
Yeah, arteries again deal with the higher pressure blood. So typically they have a thicker muscular wall to them as well. Again, I've done a pretty poor job of drawing this, but let's take a look at the pretty pictures from your textbook. Here we see a nice collaborative picture, but let's work our ways through. Again, starting first from that tunica intima or the tunica interna, we have that endothelium, which is a part of the, which is continuous with the endocardium, that simple squamous epithelial tissue, and an areolar connective tissue. But remember, as we also mentioned, in our arteries, we're going to have an internal elastic membrane. Middle layer is the tunica media, a circular layer of smooth muscle controlled by the sympathetic nervous system. And again, in our tunica media, not only is this layer typically thicker in arteries, but also in our arteries, we have our external elastic membrane in this region. And then the tunica externa, or what is also known as the tunica adventata, which is a fibrous connective tissue outer layer. We've done it with my ugly pictures. We've done it with the pretty words, but let's actually look at the pictures from your textbook. Here we have their illustration of what this looks like. And we can actually see granted, a low magnification light microscopy, but the one nice thing about it is we can see all of the artery and all of the vein. And notice there are two things that should jump out at you right away as you look at this. As we mentioned earlier, the muscular wall of an artery is going to be much, much larger than the muscular wall of a vein. But what's the other big difference you see when you look at this right at the start?
The vein has more lumen.
Absolutely, right? Typically, blood vessels at the same level. Veins have a much larger lumen than the artery. Why?
They're handling a lot less pressure.
Exactly. Pressure is what makes the world go round. Absolutely. Veins don't have the direct connection to the pump of the heart. They're typically much lower pressure, and often they have to fight gravity to get back to the heart. So they have to work extra hard. And so by having a larger lumen, there is less resistance and flow can be easier. So with less resistance, we get a better flow. Arteries dealing with that higher pressure blood, so it needs that thicker muscular wall. But because it has that high pressure, it doesn't need to worry about having such large lumen. Notice the other thing that I really like about this picture, like I said, normally when I show these things on the exam, it'll be a higher magnification so we can see the individual layers. Our illustration does a pretty good job of showing this. Again, so here we see the simple squamous. No, I don't like that. The simple squamous epithelial tissue, the areolar connective tissue, the tunica media, the tunica externa. But notice here with our artery, even at a low magnification, we can see that dark line of the elastic fibers right near the lumen. And another really distinct dark line on the outer surface of the tunica media. We can see that internal and external elastic membranes. And because it has that elasticity, one of those things you're always going to be trying to do on an exam is you're going to look for things that are dead giveaways, things that are going to help you really quickly, right away, figure out what something is. One of them is definitely these two layers of the elastic membrane. But notice as we look closely here at the illustration, you can see that the epithelial tissue has kind of a ruffled or a scalloped appearance. The reason is because arteries are under higher pressure. So when we cut it to put it on a microscope and all the blood drains out of it, there's no blood forcing it open anymore. And so it starts to recoil. And as it starts to recoil, you get this scalloped edge to the epithelial tissue. That scalloped edge is a dead giveaway, or that pleated appearance is a dead giveaway that you are looking at an artery. Conversely, when we look at that vein, notice instead, its epithelial is very, very smooth. It has that massive lumen that we talked about, a much thinner muscular wall. It often, but doesn't always, have a larger tunica externa, but it doesn't always have to either. And very little elastic fibers. Some of the larger veins will have some elastic fibers. Notice we can see a little bit of dark lines here and there, but nothing like we see in the artery. So there can be scant membranes, but they're not going to be nearly as distinct as what you see in an artery. All right. Questions on that? All right, I think that is a good stopping point. We've gotten through the microscopic anatomy of this, and we can start more talking about some of the other differences and characteristics, arterioles, capillaries. There are actually 3 different types of capillaries we got to talk about. So there is still some more anatomy we want to cover, but I think this is the stuff that I wanted to get through for today. So excellent. So any questions on the basic anatomy, the 3 layers, the 3 tunics of our arteries and veins and how they differ? All right, excellent. Then that is everything I wanted to cover for today. We finished a few minutes early, which is perfect. But we made it close to the time, so you got most of your money's worth out of this. So excellent. So study hard, look at this material, make sure you get your homework done, and I will see you on Thursday. All right, any questions? All right, have a good day.
Thank you, Professor.
Thanks.
Thank
Bye.
you.